What you're looking at is the black body radiation curve. The x-axis is color or frequency. The y-axis is power or intensity. When a hot object like a campfire coal or the sun glows because of its own heat, the distribution of the color and the intensity always follows this curve. This curve always has the same shape. Oh, at higher temperatures it gets taller and it moves leftward towards the blues. And at lower temperatures it gets shorter and it moves rightward towards the reds. But the shape is always the same. And the shape of that curve is pretty interesting. It's an x-squared curve on the low frequency red side, but it's an e to the minus x curve on the high frequency blue side. It's strange enough that a single process would be described by two different equations, but it's that hump in the middle that's the really interesting part. We knew almost nothing about this curve until the late 19th century. It wasn't until 1890 that our measurement technology finally got good enough to map out just the high frequency side of the curve. The low frequencies remained a mystery for several more years. In 1896, Wilhelm Wien came up with an e to the minus x-based formula that approximated the high energy side of that spectrum. He called it Wien's approximation. But as measurement technology improved and the lower frequencies came more and more into view, it became clear that Wien's approximation became less and less accurate the more towards the red side of the spectrum we went. Wien had a friend whose name was Maxwell Planck, and Maxwell Planck decided that he'd try to tackle the problem. He played around with a few ideas, but never really got anywhere. Then, in 1900, he decided to try a trick that he'd read about in a paper written by Ludwig Boltzmann in 1877. Boltzmann, you see, was trying to calculate the entropy of a gas, and he used a technique common amongst mathematicians. He assumed that each molecule within that gas had an energy that was an integral multiple of some constant. No fractions of that constant were allowed within his calculations. In short, Boltzmann assumed that the energy of the gas molecules was quantized instead of continuous. Boltzmann reasoned that if he made the constant of quantization small enough, then he could come up with a reasonable approximation for the entropy in a gas. This worked pretty well for Boltzmann. It gave him a decent approximation, and that approximation helped him later to completely eliminate all the quantization and use continuous energies instead. Planck hoped for the same kind of help, so he applied a variation of Boltzmann's trick. He assumed that radiant energy could only be emitted or absorbed in integral multiples of some constant proportional to the frequency of that radiation. Or, to state it mathematically, E is equal to NVH, where E is the energy of the radiation, N is some integer, V is the frequency of the radiation, and H is the constant of proportionality. Nowadays we know that as Planck's constant. This formula fit. The quantization was a compelling explanation for why the low part of the graph followed an x-squared curve, but the highs cut off with an e to the x decay. Indeed, the formula fit too well for Planck's tastes. He thought he was making an approximation, but it didn't look at all approximate. Nowadays, we don't consider it to be an approximation at all. We consider it to be a law, Planck's law. The closeness of the fit was quite disturbing to Planck, because Planck did not believe that energy was quantized. He thought it was continuous. And the fact that his formula fit so well caused him to wonder whether or not it was the mechanisms of absorption and emission that were quantized. In other words, Planck felt that the fact that atoms only belched forth or swallowed energy in discrete chunks had more to do with the atoms than with the energy itself. It was Einstein in 1905 who changed all of that. This was Einstein's golden year, the same year he published his special theory of relativity.
The paper that changed everything was entitled "On a Heuristic Viewpoint on the Production and Transformation of Light." In this paper, Einstein coined the term light quantum, and he suggested that energy itself was quantized.
What an incredible thought. Energy, the motive force of the universe, comes in discrete little packets that can't be further subdivided. This thought is so radical that even Planck didn't accept it until 1908. That incredible idea, which won Einstein the 1921 Nobel Prize, changed everything. Without that idea, there could not have been a transistor, the fundamental unit of our electronic empire. What would our lives be like without transistors? But here's the real irony. That thought that came from Einstein's own mind has sown the seeds of destruction for his other great theories, the theories of relativity. Because relativity and quantum mechanics are about as incompatible as two theories can be. One demands that the universe is a continuous curvature of space and time. The other demands that the universe is made up of pixels. One or the other, or both, are going to have to change. But we'll leave that discussion for another time.